My name is Jialei. I am a PhD student at the University of Cambridge, currently also working at Loclab Consulting in Germany. It all fits within the little CBIM kind of network. And today I'll present the review part of my work, which is the potential for creating a geometrical digital twin of road surfaces using photogrammetry and computer vision. So let's get going. Just some background. I'll be very quick because we all are in this space, but we all agree that roads are important. We all agree that we probably should manage the roads better. And a lot of you will also agree that digital twins would be a great tool for doing that. And I won't go into detail of why, because I'm preaching to the choir. But I can make an argument that because there are a lot of different types of digital twins, but I can make an argument for that 3D geometry can very much be a basis for a digital twin because it allows, intuitive interaction with the model. And if you're going to train a lot of people to use something, it better be intuitive. So the first problem in going into this was that when you talk to people working in road maintenance, road operations, etc., everyone agrees that something needs to be done, but no one knows exactly what they need in terms of a 3D model. So that was actually the first part of the project that had to be done. We had to find what are the end user requirements. So we went in doing interviews with industry practitioner, government agencies, etc., to derive both quantitative, i.e. Requirements related to the actual geometry of the model, and then qualitative. Is this auto? Oh, never mind. Okay, I might just be touching things. Related to how the person interacts with it, what kind of information it needs, scale, data lightness, etc., etc. And we also looked at exactly what needs to be modeled. So you have a road, which assets needs to be in a geometrical digital twins? And to just say it roughly, we split the type of assets up into street furniture and then the things that are on the drivable road itself. And then having one set of user requirements, one set of things that the user requirements apply to, we then looked at, so to what degree does industry actually meet these things? And the quick answer is that modeling methods or models either do not meet the geometrical requirements but are cost effective, or they do meet these requirements but they're not cost effective, at least to use at a larger scale and to increase uptake compared to what it is now. So knowing this, we found that a scalable solution is required. So looking at the levers that we can affect, quality is fixed because we've derived the end user requirements. The cost of labor can be affected by increasing the amount of automation, so decreasing the amount of labor, or you can remove or greatly improve often a barrier to entry, which is the cost of data collection, because traditionally very detailed models are collected with LiDAR scans, for instance. So then we decided to look at the use of image and video data to generate geometrical digital twins of roads with a focus on the road surface. And the reason the road surface is chosen is because it's a non-standard asset type, which is the group of assets that is least automated, and so many assets that exist on a road are described in relation to the road surface or the road center line, which is encapsulated in the road surface. So then looked at different methods to kind of what's out there right now. So first is actually segmenting the 3D point cloud. One can use photogrammetry or videogrammetry or one of its many off-branches of technologies to generate a 3D point cloud. And because it is a spatial data set, you can apply methods used for LiDAR segmentations. But then you're not taking advantage of the data that's in an image. Others, raster-based methods, they have the point cloud, and then they just kind of treat this as an image, and then segment it using image segmentation methods. But then you're kind of going around, right? So it's not very efficient. There's been attempts to fuse photogrammetric and LiDAR point clouds, but they haven't offered a better results than just purely using a LiDAR. And you can also just take an image, forget photogrammetry, just take an image and then use a neural network to project its depth and then segment that image or segment image and then project it. But the issues there is that often the depth isn't always completely accurate, and it also limits the range. So it's not very reliable at the scale of roads. So the method that looks the most promising and that I've landed on is label propagation, which is because you have images, you have a segmented image, and in photogrammetry, you can know which points in the image correspond to the point in 3D. So if you have the coordinate of a pixel, you have the segmented label. So here is an example of someone that's used that. Then if you're going to make a digital twin of something, it has to contain some kind of information. Specifically, if you're making it into open data format like IFC, you need the asset relationships. So there are several methods that have gone to use that, such as limiting a region of interest and searching, using prior knowledge to inform, or conditional random fields, which is just probability to ensure consistency in your segmentation. But these are all quite limited because they are handcrafted, so they can't be applied to a larger context. There are also deep learning methods such as a latent hierarchical part-based method, which basically is a typograph-based method that can find the relations between different assets in a scene, and then those could potentially get exported later into IFC with relationships in it. And then lastly, once you have your segmentations, once you have your relationships, you'll want to convert into an actual model. The thing is that there's very little work on this. There's no image to model pipelines. Some methods have been tried, such as using raster-based methods to find the geometry of street markings and converting those to polylines, which can then be put into GIS, for instance, or having a segmented point cloud and just extracting, for example, the road width from the point cloud itself. One work I want to highlight is the work by Soilan, I don't know if I'm pronouncing that right, that did this for both rail and roads, but from LiDAR. And what was found here, and what was found across everything, is that the current methods, when applied to rail, work a lot better than applied to road, and that's because rail is a lot more uniform. So it's a lot easier to find a cross-section that you keep going with. Whereas with roads, they merge, they go off in all directions, there's crossings, etc. So current methods really struggle with this kind of being generalized enough. So the main gaps, to summarize, is that the segmentation methods have only been roughly explored, and crucially, there's not really an inclusion of road markings. Other methods for segmentations, as discussed, they struggle a lot with more complicated layouts and also have a very limited amount of assets. And so we see that there's a tension between the level of detail and also the level of scale that you need for roads. So out of this, I got three kind of concepts to work with for the rest of the PhD. So the first is to try to use image segmentation to segment a point cloud, and hopefully that will improve the quality but also decrease computational effort. The second is to address the tension between scale and detail, to just split it up, because roads can be complicated, but they can also just be one straight road for many kilometers. So apply what's needed to where it's needed. And the third one is that we can try to use graph methods to find relationships to export, but of course these are all very, ambitious things, but hopefully these can provide some directions for future research and my research, yeah. So that's me. Thank you for your time, and if there are any questions, I will try my best to answer them.